Alright guys, it's Charlie Tango 1994 back with another YouTube video.
Standing wave ratio, or SWR, is a mathematical expression of the non-uniformity of an electromagnetic field, or EM field, on a transmission line such as a coax cable. Usually SWR is defined as the ratio of the maximum radio frequency, RF voltage, to the minimum RF voltage along the line. This is also known as the voltage standing wave ratio, VSWR. The SWR can also be defined as the ratio of the maximum RF current to the minimum RF current on the line, current standing wave ratio, or ISWR. For most practical purposes, ISWR is the same as VSWR. Under ideal conditions, the RF voltage on a signal transmission line is the same at all points on the line, neglecting power losses caused by electrical resistance in the line wires and imperfections in the dielectric material separating the line conductors. The ideal VSWR is therefore 1/1. Often the SWR value is written simply in terms of the first number or numerator of the radio because the second number or determinator is always 1. When the VSWR is 1, the ISWR is also 1. The optimum condition can exist only when the load, such as an antenna or a wireless receiver, into which RF power is delivered, has an impedance identical to the impedance of the transmission line.
If you're new to this channel and would like to see more CB related videos, feel free to hit the subscribe button below and watch out for new videos uploaded every Wednesday. If you enjoy my videos, don't forget to hit the like button or leave me a note in the comments section. Also, if you're new to CB Radio, watch this video through to the end to find out more about the free gift I offer to all of my subscribers.
This means that the load resistance must be the same as the characteristic impedance of the transmission line, and the load must contain no resistance, that is, the load must be free of impedance. In any other situation, the voltage and current fluctuate at various points along the line, and the SWR is not 1. When the line and load impedance are identical and the SWR is 1, all of the RF power that reaches a load from a transmission line is utilized by that load. When the load is an antenna, the utilization takes the form of EM field radiation. If the load is a communications receiver or terminal, the signal power is converted into some other form, such as an audio-visual display, if the impedance of the load is not identical to the impedance of the transmission line. The load does not absorb all the RF power, called forward power, that reaches it. Instead, some of the RF power is sent back toward the signal source when the signal reaches the point where the line is connected to the load. This is known as reflected power or reverse power. The presence of reflected power, along with the forward power, sets up a pattern of voltage maxima, loops, and minima, nodes, on the transmission line. The same thing happens with the distribution of current. The SWR is the ratio of the RF voltage at a loop to the RF voltage at a node, or the ratio of the RF current at a loop to the RF current at a node. In theory, there is no limit to how high this ratio can get. The worst case scenarios, highest SWR values, occur when there is no load connected to the end of the line. This condition, known as an unterminated transmission line, is manifested when the end of the line is either short-circuited or left open. In theory, the SWR is infinite in either of these cases. In practice, it is limited by the losses but can exceed 100. This can give rise to extreme voltages and currents at certain points on the line. The SWR on a transmission line is mathematically related to, but not the same as, the ratio of the reflected power to forward power. In general, the higher the ratio of reflected power to forward power, the greater the SWR. The converse is also true. When the SWR on a transmission line is high, the power loss on the line is greater than the loss that occurs when the SWR is 1. This exaggerated loss, known as SWR loss, can be significant, especially when the SWR exceeds 2 and the transmission line has significant loss to begin with. For this reason, RF engineers strive to minimize the SWR on communication transmission lines. A high SWR can have other undesirable effects too, such as transmission line overheating or breakdown of the dielectric material separating the line conductors. In some situations, such as those encountered at relatively low RF frequencies, low RF power levels and short lengths of low loss transmission line, a moderately high SWR does not produce significant SWR loss or line overheading and can therefore be tolerated.
Hope you enjoyed watching this video, and as a thank you to you, particularly if you're new to CB radio or returning to it after many years, I've put together a free information series called The Beginner's Guide to CB Radio, which I'm sharing with all of my subscribers. To find out more, click the link in the top right corner now.